I would like to present today a topic that is very close to my heart, and I hope I will convince you that it is very important to all of us. So the topic is bioprinting and prosthetic and how we can turn rehabilitation challenges into a national innovation mission. And the last war left Israel in unprecedented number of soldier amputees. And the good thing is their lives were saved, but now they have to continue their life without a hand, without a leg, without both legs, sometimes without both legs and hands, and this really surprised us just to understand that Israel doesn't have a solution for these soldiers and cannot provide the state-of-the-art treatment to these soldiers, and many of them need to travel abroad to spend months and without their family to adjust the right prosthetic device, and it's not one time, you need to go again and again. And we were really surprised to see that Israel is really not advanced in this field, and we started to think how we can advance prosthetic research here and can we make it a national priority. And the thought was that it left us really unprepared, but maybe we can now turn it into an opportunity and bring Israel to the front of this research direction, not only the prosthetics themselves, but this can be actually the beginning or the center of something that could lead to solutions, more general solution in advanced human mobility, and to make Israel a leader in this field. And actually human mobility, when we think about it, enhanced human mobility, really add several disciplines together, is integrating biology and engineering and data science and AI, something that was mentioned in the morning, the bioconvergence and all this. So it's really something that is the right timing maybe for us to get into this train. So when we're talking about the prosthetic devices, the current ones are really, some of them are really, really not advanced. And you can see some of the hand limb, the upper limb solution that are really body-powered and not advanced. And some of the lower limb, the leg devices are sometimes more advanced, and some are motorized or have some robotic elements, but still many of them do not provide enough solution. They are short on power, comfort, adaptation, and there's still a lot to do to make them something that the soldiers and then the patient can use and have a really better life. So you can see some of the major challenges that both the amputees, the prosthetic users, and the developers face. You can see one of them is all the sockets and the liner, how to really connect the prosthetic device. You can have a very advanced one maybe, but how you really connect it to the body, this is a real challenge. And a lot of, it's very painful sometimes, and many just decide, okay, I will not use it because it's so uncomfortable. Many biomechanical limitations, cognitive and control, how you can really, it's a lot of burden, both physically and mentally, to use a prosthetic device. No sensory feedback so far, and really the cost and access, and how you can really train people to support the rehabilitation process, starting from the amputation itself and then treating the patient. So the thought that a group of people, we called it Marching into the Future. The initiative is all volunteers and coming from different disciplines, trying to think how we can advance Israel in this direction. And we thought about maybe coming together with a National Institute for Research, and also to connect it to a clinical innovation and implantation division. And in between, of course, we have all the industry that need to come together and translate all the new technologies, have also rapid prototyping cycles, so we can bring it much faster to the amputees. And it can be an integrated national ecosystem, providing the urgent clinical need, but also thinking about a longer solution longer system, something that really bring Israel to the front. And if we think about 10 years from now, we can see Israel, we hope to see Israel at the front, bringing the best solution for this, for prosthetics, but also for enhanced human mobility that can be relevant also to the army, to the agriculture, to many things if you have systems that can provide better human mobility. So this is the vision. And when you think about the future of prosthetic, so you can really see how many disciplines can come together, how you integrate it to the body, how you can put many sensors, smart materials that can provide antimicrobial surfaces, embedded sensors, very light, hopefully, how you can now have the interface of the human-machine or brain-machine interface to provide also the sensory robotics, AI, how the prosthetic device can learn the behavior and adjust accordingly. So many things now are on the table, and we just need to come and integrate them together. The last thing is maybe robotics, the advanced robotics that we see it's everywhere, but how we can implement it to the prosthetic device, and how we can use tissue engineering and bioprinting to integrate it with the body. So when we're talking about integration with the body, this is just an example, the osteo-integration or the osseo-integration, where you can connect now the prosthetic to the bone itself by inserting a metal screw to the bone, and then with a click, connect to the prosthetic device. So this is something that is starting now to get in, but can we dream about something that will be fully covered with the tissue? How we make sure that we don't have infection in the boundary between the prosthetic and the bone and the skin? So there are many things that can be improved to have something that will mimic better the tissue. So if we're talking about this interaction with the body and the dreams about how we can implement tissue engineering and bioprinting, so this is something that we hope to be able to add something into it in our work with bioprinting. So in the last years, we developed bioprinting technologies to create a large tissue construct, and this is an example of a bioprinter where we have special bioinks that can now build the tissue layer by layer and also seed the cells into it. And with this technology, we're able to engineer a large muscle tissue construct. You can see it here in the cover of the journal. And this is a large piece of muscle that can really treat volumetric muscle loss. So a large piece of muscle that is missing now can be repaired with a printed muscle. And for this, we realized that we have to integrate large vessels, so to feed the construct and be connected to all the small capillaries, so we can really feed it in the lab and also in the body. And this is an example for this connectivity between a large vessel that is bioprinted and the tissue with all its vasculature that allow us to bioprint and grow the large tissue construct. So you can see here this bioprinted construct with the vasculature, the connection between the vasculature. You can see the connectivity between sprouted coming from the large vessel to the smaller vessel. And everything that is being perfused through the large vessel will reach everywhere in the tissue. And for this, we can now really create these tissue flaps. And you can see it here, the tissue flap that now can be implanted and connected, in this case, to the artery. And you can see the implantation, bioprinted muscle, implanted, and fully perfused. So the next thought is, can we now make composite tissues that is not only bone, not only muscle, but bone, muscle, fat, skin, everything that allow us later to repair large defects and maybe code even prosthetics. So this is an example of bioprinted fat tissue, now printed in one step with its vasculature. You can see the colors of the vasculature, the large vessel, the smaller vessel, everything connected. We're building a bioreactor that can perfuse the tissue in the lab. And as you see in the images, all the green dots and the white dots are actually showing us that the fat cells are really happy there and fully vascularized. You see the blood vessels, and you can see the cells integrated in between with the lipid droplets inside. And the next step is to develop this printed tissue with muscle and fat together. So this is a product that I show here, muscle and fat, and also connection to artery and vein. So this allows us to make larger tissue construct and connect them to to the right place. And everything you have there, you have the muscle, you have the fat, you have the lymphatic vessel, we have the blood vessel, everything is bioprinted together to provide the right tissue construct that can be fully integrated in the body. And this is how it looked when before the implantation. We suture it, we can suture it to the artery and to the vein. You can see the relatively large piece bioprinted, and this is the hope that now we have the tool and we can go larger. And this is an example of how we going larger. It's a work that we're doing now in a sheep model for facial reconstruction to reconstruct large piece of tissue. And you see the bioreactors, you see the large tissue that being bioprinted. So what I want to end here is we can bioprint vascularized tissue construct and tissue flaps, but what I want to focus here is on the question, can these bioprinted tissue flaps be used to replace missing limbs in the future, and maybe to be combined with prosthetic devices, and how we can, in general, not only using bioprinting, but using all the knowledge that is maybe here and elsewhere, how we can develop better limb prosthetics. And I will thank my group, but I also want to thank here the group of people of Marching into the Future that all volunteer and spend a lot of the time to think about solution and how to position Israel in a better place, and most importantly, how we can provide solution to our soldier. We owe them this. So if you would like to join and help to think about how we bring Israel to the front in this field, so please contact me or any of the people here, including Yaakov. Thank you.